Good evening. Tonight we are very happy to welcome Arthur Jaffe, the president of the Clay Math Institute, who is here. I think he wanted to see for himself the remarkable turnout we've been having at these lectures. Anyway, Arthur is a professor of mathematical physics at Harvard. He's a former president of the American Mathematical Society and has many honors which I won't take time to run through, but he's going to say a few words before the talk tonight. Arthur.
I won't speak for long, but I'm just very happy to be here. It's a wonderful turnout. I wouldn't have believed it if I hadn't seen it with my own eyes. I thought I'd take the opportunity to say a couple of words about the Clay Institute, but before that, I would very much like to thank Alan Reed and John for organizing this series. It's a wonderful thing that you've done. The Clay Institute, I'll just show you a couple of things from our website. And if you haven't seen it, I wanted to let you know that we don't just have the Millennium Prize problems, but there are a number of other things done by the Clay Institute. And in particular, our new website shows here the Millennium Lectures at the University of Texas, which really, we had no part in organizing, but we are so happy that we put them there. And we gauge things from the number of hits, and we get quite a few hits. This is the monthly rate, and you see it has some local peaks. And if you look at the daily graph, it actually has quite a lot of structure. And over here on February 7th, there's a little peak that I'm sure is due to the beginning of the Millennium Lectures here. Now this, I might mention that I'd like to come back to this, but our event following up the Millennium Meeting in Paris, where these problems were announced, will take place this summer on July 13th in Washington, and it will be a combination of the annual meeting with the closing ceremony of the International Mathematics Olympiad, which will bring over 500 students from 80-some countries. It has never been in the United States since 1980. This will be the second time. So if you're in the Washington area or outside, you should watch for these young, talented kids. And if you meet some of them, I hope they'll have a good impression of the United States. And many of them, perhaps, at some stage, end up here. But other thing the Clay Institute does is we do employ mathematicians. And these are the 8 long-term prize fellows. We were very happy because we just appointed Roman Bezrukavnikov, Alexei Borden, who's now a graduate student at Penn, Mustada is a graduate student at Berkeley, and Sergei Gukov is a graduate student at Caltech. He's the youngest of them, 23 years old. He has 21 publications. And I hope his future is as good as his past. But these people work between 1 and 5 years for the Clay Institute, and that's just one of about 20 programs we have in place. And lastly, we had a lecture about the P versus NP problem called Minesweeper Math, because the P versus NP problem was shown last year by Richard Kay in England to be equivalent to the computer game Minesweeper, and Ian Stewart talked about this, and here's that audience, which is about as large as this one. I'm not sure. And here's Mr. Clay, if you're interested. And this allows, the fact that it's related to this problem allows the P versus NP problem, which is regarded as one of the most esoteric, though important problems of modern mathematics, to be explained to even more people than can understand Fermat's theorem, to a significant fraction of the world's population, because a significant fraction of the world's population has played the computer game. So, so I'll stop and look forward very much to hearing the lecture. Thank you.
So our main speaker tonight is Vijaya Ramachandran. She was born and grew up and did her undergraduate work in India. Carrying on the tradition of her academic family, she went on to get her PhD in electrical engineering and computer science at Princeton. After 5 years as an associate professor at the University of Illinois at Urbana, interspersed with visits to Berkeley for special programs, she came here to UT in 1989 and is now the William Blakemore Regents Professor in our Department of Computer Sciences. But she's the only one of our speakers who is not on the math faculty. Incidentally, she is the only woman and the only native of Asia among them. But the important thing is that she is an expert in computer science. Her special research is in the design and analysis of algorithms and parallel computing. She's the editor of 4 important journals publishing research in these areas. Presumably her algorithms are P rather than NP. In any case, she will tell us about the 4th problem, millennium problem, P versus NP. She's eminently qualified to do this. Although technically, as I indicated in my remarks at the end of the last session, and as was indicated by her slide that was up before, technically that's a logical problem, but its source and its interest is entirely in computer science. And so let's hear about it. Vijaya.
So today I will be talking about the P versus NP problem, and as was mentioned, this is a problem in computer science, and in fact it's a central problem in theoretical computer science. And since it's a problem in computer science, it deals with the question of how efficiently we can compute certain problems. So during the course of this talk, I will be using quite a bit the term algorithm. And what I mean by an algorithm is simply a method that computes the correct answer for every input to a certain problem. That's all that it is. And let me start off by looking at a couple of simple algorithms that everyone knows about. The first is the standard method to add 2 numbers. So the input to this problem is 2 numbers. Let's assume that each of the numbers has n digits. In this particular input, we have 4 digits. And we all know how to do the addition. We go from the rightmost position, and we have a basic table that tells us how to add 2 single digits. So we do that. we might have a carryover. We do have a carryover here, 7 plus 4, 11. We have a carryover. Then we add the carryover to the first digit in the second position. Then a second addition with the second digit here, generate the next digit, and so on. We go all the way this way. And then in terms of measuring the efficiency of this method, what we want to ask is, as the input size increases, how many steps will the algorithm take? And we are primarily interested in the number of steps taken as the input size gets very large. Because for small inputs, we can actually do the problem by hand. So the real reason for looking for efficient methods to solve a problem is that it should be able to attack the problem well when the size of the input gets large. So in terms of the size of the input, in this case, the size of our input is 2n, because we have 2 n-digit numbers. How many basic operations does this method perform? And our basic operation will be adding 2 digits. So in the first column, the rightmost column, we do 1 addition. And thereafter, we may do either 1 or 2 additions, depending on whether or not we have a carry. So approximately 2n operations, that is, and the basic operation being adding 2 single digits, is what this method takes. So for an input of size 2n, it's taking about 2n operations, so it's taking linear time in the size of the input. And we are not going to be bothered about small constants, so we will denote this by this notation here, which says O of n time, which is some constant times n time. Okay? So that was the familiar addition method. So that's an algorithm that runs in time that's linear in the size of the input. How about multiplying 2 n-digit numbers? Again, by the standard method, the method that everyone has learned in school. Here it takes a little bit more time because we start with the rightmost digit of the multiplier, and then our basic operation is now multiplying 2 digits for which we have a table. And we start and we multiply each of the digits in the multiplicand, and that's how we generate the first row. We start with the rightmost digit of the multiplier and multiply each digit of the multiplicand and write it out in here. Then we go to the next digit. So that takes n operations, again assuming 2 n-digit numbers as the input. Then we go to the next to rightmost position. We do the same thing and generate the next row of numbers, shifted 1 position to the left. And we repeat this. And we repeat this n times because the multiplier also has n digits. So to generate all of these numbers in here took us n times n, or n squared, basic operations, which are multiplication in this case. And then we add column by column. And we can see there's roughly n squared additions in here. Okay? So totally, if we say a basic operation is either adding 2 single-digit numbers or multiplying 2 single-digit numbers, we are doing about 2n squared operations to do multiplication. So as the size of the input gets large, the running time is quadratic in the size of the input. And that I denote by O of n squared. Now, in fact, people have come up with cleverer methods of multiplying 2 n-digit numbers, which is faster than this. But for the purpose of this talk, we are quite happy that the running time is quadratic for the following reason. We are mainly interested in what are called feasible algorithms. And a feasible algorithm is simply an algorithm whose running time is polynomial in the size of the input. So linear is a polynomial where the exponent to the input size is 1. Quadratic is polynomial where the exponent to the input size is 2. And we'll say an algorithm is a polynomial time algorithm for a problem. Of course, it should be a method that solves the problem correctly on every input. And additionally, it should take no more than some constant times n to the power of some other constant. And that constant can be anything, but it has to be n to the power of some constant, bounded by the number of steps for inputs of length n should be bounded by some constant power of n, which we denote by O of n to the k. So the methods we've seen for adding and multiplying integers are polynomial time algorithms. And we basically start off with the following feasibility thesis, that a natural problem has a feasible solution, feasible algorithm or a practical algorithm, if and only if it has a polynomial time algorithm. So we're going to associate algorithms that are applicable in practice, or efficient algorithms, with algorithms that run in polynomial time. Now this is just a thesis. It has come from experience, and it was first formulated in the 60s by Cobham in the context of complexity theory, and Edmonds in the context of designing efficient algorithms. Now, throughout the 60s, I guess late 50s and 60s, people were struggling with coming up with fast methods to solve various problems. But they basically used ad hoc techniques, and they just looked at how the algorithm performed on the inputs they were interested in. And it was only in the mid-60s that this formal notion of what is an algorithm, what it means for an algorithm to be feasible and efficient came into place. And this is now firmly entrenched in the computer science community, and everyone agrees that a feasible algorithm, a practical algorithm, is one that runs in polynomial time. Of course, once you have a polynomial time algorithm, you still want it to run as fast as possible. Linear time is better than quadratic time, but there is a qualitative difference between having a polynomial time algorithm and, say, an exponential time algorithm. And we'll also say that a problem that does not have a feasible algorithm is said to be intractable. So that's just a terminology. You might have come across the term intractable problems. And all that means is that we don't know of any polynomial time algorithm for the problem. Here's a table that sort of illustrates the qualitative difference between a polynomial running time and an exponential running time. So in the first column, I've indicated how large an input size we can solve in 1 second on a currently available machine, where I've assumed that the machine can execute 100 million basic operations a second. So of course, if the running time was just n, you can solve inputs as large as 100 million, huge inputs. If it was a moderately large constant times n, 100 times n, correspondingly, the size of the input becomes 100 times smaller, because you have that factor of 100, so you can only solve a problem of size 1 million. If instead of linear it was quadratic, then it's only 10,000, considerably smaller, but still a fairly large size. N cubed, it goes down to 464. So even with polynomial, as the power gets larger, the size of problem you can solve in 1 second is going to go small. On the other hand, if you take the most commonly quoted super polynomial function, which is the basic exponential function 2 to the n, you can only solve a problem of size 26 in 100 million operations. So clearly, this is much smaller than any of these polynomials. But additionally, when you look at the next 2 columns, you'll see even more dramatically the inherent problem with an exponential growth as opposed to a polynomial growth. And here, we are looking at what happens if your computer becomes faster. And this is certainly not a far-fetched assumption. It keeps doing that regularly. So let's say it went up. We now have a computer that runs 100 times faster than what we have currently. Well, if your algorithm ran in linear time, and it doesn't matter whether it's n or 100 times n, you're going to be able to solve a problem, input size that's 100 times larger. If it is n squared, it's only going to be 10 times larger, but still, that's a reasonable constant factor times larger. For n cubed, it comes down to 4.64 times the current input size, and so on. As you get larger exponents here, the constant factor here is going to go smaller. But in contrast, look at what happens if your running time is exponential. You only have an additive term of 6. So instead of 26, if you get a computer that's 100 times faster, you just have 26 plus 6. And similarly, 1,000 times faster, you get 3 more. While if you have any polynomial growth, as your computer speeds up, there will be some constant factor increase in the size of problem you can solve. So there is a qualitative difference between polynomial growth and exponential growth. And that's one of the reasons why we call polynomial time as being feasible. And also it has turned out that in practice, even though polynomial time allows exponents like n to the 100, which is completely unreasonable and impractical, for actual natural problems, once we have a polynomial time algorithm for a problem, most of the algorithms are at most n cubed or n to the 4th. We don't see natural problems for which we have a very high polynomial running time. So there are all these features that reinforce our belief that feasible algorithms should correspond to polynomial time algorithms. So that is certainly a basis for the P versus NP question. Okay, so now let's look at a somewhat different problem, which you may not have seen. And it's from a different domain. It's from the domain of graph theory. And the problem is called Euler-Tour. So first I need to tell you what a graph is. So a graph is just a structure that has two sets, a set V, which is a set of vertices, and a set E, which is a set of edges. And each edge is just a pair of vertices. It's something that connects a pair of vertices. And if your graph is small, you normally just depict it by a nice little picture. So here's a picture of a graph with 5 vertices. So the black dots are the vertices of the graph. There are 5 of them, A, B, C, D, E. And since each edge connects 2 vertices, I've indicated the edges by lines joining 2 vertices. So this is the edge AB. Then you have an edge BD, CD, AC, CA, CE, EB, and CB. So this graph consists of 5 vertices and 7 edges. Okay? And the Euler-Tour problem. So first, what is an Euler-Tour in a graph? So a graph has an Euler-Tour if it is possible to walk along the edges of the graph, starting from any point, but from point to point along the edges of the graph, and return to the starting point, but return to the starting point by traversing each edge exactly once. Okay, so for this graph, you may want to look at it to see whether it has an Euler-Tour. And in fact, it does have an Euler-Tour, and I've just labeled the edges in the order in which you would traverse them if you started from vertex A. So I take this edge first, second, third, fourth, fifth, sixth, seventh. So I go through every edge by just following a sequence of edges and get back to the starting point. So you can ask, so an interesting question is, can you design an algorithm which, given an input graph, determines whether or not it has an Euler-Tour? And this problem was formulated by a very famous mathematician called Euler. And he is famous for many things. He's made important contributions in analytical geometry, trigonometry, calculus, and number theory. But this particular problem was formulated strictly as a recreational activity. Even though, as a result, it's generally considered to have started the whole field of graph theory. So why did Euler look at this problem? It has to do with the following puzzle. There was a city called Königsberg, and through the city of Königsberg flows a river called Pregel. And in Euler's day, there were several bridges across the river, which are denoted in red here. In particular, there are 7 bridges in here. And it used to be a common point of, I guess, conversation among the people living there to ask one another whether it's possible to start it from their house, let's say the house is down here, and cross each of these bridges exactly once and return to their house. And, people tried, and apparently, no one succeeded, and no one was sure, whether some other clever way was possible, and so on. So Euler came to hear of this problem, and here's what he did about it. So here I just have the same, the essential features of this, the bridges in here. So you can see that the river Pregel comes and it forms the island A that corresponds to this, and then forks off, forming the region D. And then you have the region below the lower part of the river, that's B, and the island, which is C. And he said, well, the essential information that I need here can be captured in the form of this graph structure here. I'll put in a vertex for each of these regions, and I'll put in an edge for each bridge. So you can see that there are 2 bridges connecting A and B, so we actually have 2 edges between the same pair of vertices. So this is strictly not a graph, it's something called a multi-graph, but we won't worry about that. It's almost like a graph. Similarly, between the region A and C, again we have 2 bridges. So we have 2 edges in here, and you can see between region C and D we have this bridge, and similarly between A and D we have this bridge, and B and D we have this bridge. So we have this graph. So we can translate that question into the Euler-Tour question on this particular graph. does this graph have an Euler tour? Can we start at, say, the point B and traverse each edge exactly once and return to B? Well, that still leaves the question of how you solve it. So how would we solve this Euler tour problem? Well, one way to do this would be to just do a brute force search. Try every possible way of traversing the 7 bridges. So you pick a starting bridge that you start with, and then each of the remaining 6 bridges, you try every possible ordering of them and see whether that's something that you can do. Because you just have to check for the next bridge, am I in the right position where I can cross that bridge? And if I'm able to do it for all 7 bridges and get back to the starting point, then I have found a solution. So how many such orderings are there? So we fixed the first bridge, but that still leaves 6 bridges. And there are 6 factorial orderings, which is 720, which is really not that much by today's standard, but must have been quite a lot in 1736 when you had to do everything by paper and pencil. And for each such ordering, you have to check whether it's a legal ordering, which you can do in 7 steps to see whether. So you're talking about this times 7. That's the number of operations if you were to make this into an algorithm. But if you were to make it into a general algorithm where the input graph had m edges rather than just 7 edges, it would give an m factorial time algorithm, which is certainly greater than m over 2 to the power of m over 2, which is, say, greater than 2 to the m if m is greater than 8. So this is not a feasible algorithm. It's an exponential time algorithm. So is that what Euler did? No. Instead, he came up with this very simple observation that he proved that a connected graph has an Euler tour if and only if every vertex has an even number of edges incident on it. And now, if you go back to our Koenig's big bridge problem, this graph completely does not fit the bill. I mean, it would have been enough for it just to have one vertex of odd degree, but every vertex in here has odd degree. And it's really not that difficult to prove this theorem, but let's not go into that. You may want to think about it. At least it should be easy to see that if a vertex has odd degree, you're not going to have an Euler tour. And the reverse, if every vertex has even degree, then you can actually find such an Euler tour. It requires a little bit more thinking. But for our purposes, with what we want to note here is that once Euler had this very nice insight about the nature of Euler tours, it made the problem feasible because it now has a very nice algorithm. It just takes linear time in the number of edges. So now it's no longer, it was, before Euler's time, it was an intractable problem, then it became a feasible problem. Now here's another problem from another different domain. Yeah, we're going to see a lot of problems in this talk because it's all about, this P versus NP question is about computational problems. So yeah, so now this is in the realm of Boolean formulas. So here's an example of a Boolean formula. It's just like an arithmetic expression with variables, except that instead of plus and multiplication, we have the symbol which looks like a V, which stands for OR, and the symbol that looks like an inverted V that stands for AND. And they have the natural meaning that we associate with OR and AND in everyday English. And additionally, you have these X, Y, Z, which are variables. And you may also put bar on top of a variable, which just means that that's the negation of the variable. And this is a Boolean formula, which means that each of these variables can only take one of 2 values. Traditionally, we call that 0 or 1, and we associate 1 with that variable being true and 0 with that variable being false. So if you have truth and falseness associated with each variable, then the OR of 2 variables is true if either of them is true, and the AND of 2 variables is true if both of them are true. And the bar just indicates the negation, which means that if Y is true, then Y bar is false, and vice versa. If Y is false, Y bar is true. And now the Boolean formula evaluation problem just asks the following question. Suppose you're given a Boolean formula, and also you're given values for each of the variables. What would be the value of the whole formula? Once you give values for the variables, you can then apply the rules for the bar and the OR and the AND, and evaluate either the whole formula to become either a 0 or a 1. And what is it going to be? So here is an example problem here. And I've used Boolean formula here in a particularly simple form, which I'll call AND of ORs. So you can see that you have groups of variables and their negations connected by ORs, and these groups are connected by ANDs. We'll call that ORs, AND of ORs. And then I've just considered what happens with the assignment x equals 1, y equals 1, z equals 0. And this is a pretty easy problem to solve, pretty straightforward to solve it. First thing we do is, we are given this as assignments, we just plug in the values. And that's what I've done in this line. X was 1, y was 1, z was 0. So I have that here. And then 0, 1, 1, and so on. So I have this in here. And then in the next line, I just go through all the ORs. All that I need to check here is there at least 1, 1, in which case it evaluates to a 1. So this evaluates to a 1, this evaluates to a 1. Here you have all 3 zeros. So this becomes a 0, and this becomes a 1. And now this is an AND, and since you have a 0, it evaluates to a 0. Okay? And you can see that this basically took linear time at this point. The size of this formula is the total number of symbols here. I did one pass to plug in the values. I did a second pass to evaluate all the ORs. Each of them took n steps. And then a third pass, which took less time, but certainly no more than n time, to compute the AND to get the 0. Okay? So this is a linear time. So this problem is in P. So I can keep going with more and more problems. But instead, I said this problem is in P. This problem can be solved in polynomial time, because I've not yet defined P, which I'm going to do right now. So what is the P in P versus NP? It's basically problem solvable in polynomial time, except that we are going to confine our attention to decision problems. That is, problems with yes-no answers. So the Euler-Tour problem, does the graph have an Euler-Tour? Yes, it does. No, it doesn't. And similarly, Boolean formula evaluation problem. Does it evaluate to 1? Yes or no? So a decision problem, which we'll also sometimes call a language, is a problem with just yes-no answer. Okay? And so these two problems that we've seen are decision problems or languages. And the class P in the P versus NP question is the class of languages that are solvable in polynomial time, that have an algorithm, that have feasible algorithms. Okay? So that takes care of half of the P versus NP question. So now let's move on to what NP is about. And again, we are going to see a few more problems for that. Okay. So next problem is another graph problem. It's called the Hamiltonian cycle problem. And so here, a graph has a Hamiltonian cycle as opposed to an Euler-Tour. And read this definition carefully, because it looks very similar to the Euler-Tour. A graph has an Hamiltonian cycle if it is possible to walk along the edges of the graph from vertex to vertex and return to the starting point by traversing each vertex exactly once, as opposed to each edge. Okay? So for example, I have here two graphs in here. If I look, so these are two separate graphs. If I look at the graph on the left-hand side, my left-hand side, it has 4 vertices, and it's very easy to see a Hamiltonian cycle. I just need to find a cycle that goes to each vertex once and comes back. And so it has. And this graph, I'll let you stare at it for some time. It doesn't have a Hamiltonian cycle. And you can just try all possibilities and see that it doesn't have one. And this problem owes its name to another famous mathematician, William Hamilton, very eminent Irish mathematician, who's famous for his work on quaternions. But the Hamiltonian cycle was strictly a recreational thing for him. Or rather, it was actually a business thing for him. He made a puzzle based on the Hamiltonian cycle problem. And here's the puzzle that he made. He called it the Icosian problem. And in the process of making the puzzle, he defined this problem. He called it the Icosian problem. And so he used this particular graph. It's just the dodecahedron just squashed in on the thing. So, but we're just going to view this as a graph. And he actually manufactured an actual puzzle in which he had a hole for each vertex. And then he gave 20 pegs that were connected with string. And the player had to put these pegs into the holes inside, and he had drawn the dodecahedron on the puzzle. And they had to put the pegs on the different holes in such a way that the strings went along the edges of the graph. And that would correspond to a Hamiltonian cycle. And so does this graph have a Hamiltonian cycle? Hard to tell, but it does have. And let me show you, even though it's difficult to see. So here's the Hamiltonian cycle. I'll put it slightly offset. First of all, let's see that this is a cycle. You can see that I started from here. And it connects up all the vertices and returns to the starting point. So it is a cycle, but is it a valid cycle? I can do that by seeing that all of the blue edges fall on edges of this graph. Okay? So it's actually quite a clever puzzle that he designed, though apparently it was a complete flop as a business proposition. So he didn't make any money with it. So this is where the Hamiltonian cycle problem was formulated. And again, we can ask, just as we asked for the Euler-Tour question, we can ask, how would we solve the Hamiltonian cycle problem? That is, given an arbitrary input graph, does it have a Hamiltonian cycle? Again, we can use brute force, just as we did with Euler-Tour. Try all the, pick any one vertex as a starting point. Try all the n-1 factorial permutations of the remaining n-1 vertices. And for each of those, check if there's an edge between each successive pair and an edge between the last vertex back to the first. And if there is, you found a Hamiltonian cycle. If after you've generated all n-1 factorial permutations, none of them gave you a cycle, then you can say, no, it doesn't have a cycle. Okay? So you have a brute force method, but it's clearly not polynomial, because n factorial we saw earlier was not polynomial. But here's the difference with the Euler-Tour problem. For this problem, no one knows how to solve this in polynomial number of times. Not to say, for polynomial number of steps, not to say that there isn't one, but we don't know how to do it. And we don't know whether we're just not clever enough or there's some inherent reason why we haven't got a polynomial time algorithm. Now, a problem that's closely related to the Hamiltonian cycle problem is the traveling salesman problem, which I'll call TSP, which is probably the most famous problem in the P versus NP, in connection with P versus NP. So you might have heard of this problem. And the problem is the following. The problem really, the informal statement of the problem is you're given a salesman who needs to visit n cities. And there's a cost for traveling between each pair of cities. Okay? And the salesman has a certain budget. Is there a way for him to make a round of all the cities, visiting each city exactly once, returning to the starting point, and still stay within his budget? Okay? And that we can formulate as the graph problem I've listed in here. So the cities are the vertices of the graph. And we put an edge. And I've just put, I haven't put the entire graph. Where I haven't put an edge, it means it's too costly. So you just can't go that way at all. So here you have a graph. And between each pair of vertices for which there's an edge, there's an associated cost. And the budget is, in this case, is 30. And the question is there now, in terms of graph theoretic terms, what we want is a Hamiltonian cycle in this graph. But now we want to sum up the weights on the edges in the Hamiltonian cycle and ask if that sum is less than that target budget that you have. And in this case, you can see that this is the same graph I had before, for which we said this is an obvious Hamiltonian cycle. But that's not going to work for the traveling salesman because that's too costly. 20, 25, you've exceeded the budget. But still the answer is yes here, because there's a different Hamiltonian cycle which does stay within the budget. Right? So it's a very similar to the Hamiltonian cycle problem, but this is again a problem that arises in the context of P versus NP. And again, you can ask the question, can we solve this problem? Well, we can certainly solve it by brute force, similar to Hamiltonian cycle in n factorial steps. Again, here, no one knows how to solve it in a polynomial number of steps. And here's a third problem along the same lines. And that's satisfiability, which I'll abbreviate to SAT. And that says, given a Boolean formula, and specifically a Boolean formula that is an AND of ORs. And that was the example we saw earlier, which in the evaluation case. But here, it's not evaluated for a certain values for the variables. You ask, is it satisfiable? And what that question asks is there a way of assigning zeros and ones to the variables so that the formula evaluates to 1? Okay? We can solve that, again in exponential time. Let's say it had n variables, the formula had n variables, and its size was m. Then you try all the 2 to the n possible values for the variables, because for each variable you can give either 0 or 1, and there are n of them, so you have 2 to the n assignments. And once you give an assignment, the evaluation problem we saw was linear in the size of the input. So we can do it in this number of steps. Now n is clearly less than or equal to m, so this is exponential in m, but not necessarily polynomial unless you had a very small number of variables. In the general case, it's exponential. And again, this is a problem that no one knows how to solve in a polynomial number of steps. Okay, so you can ask, well, these problems, are they in P? The answer is we don't know. However, these problems do have a certain structure about them or certain property about them. And the key property that they have, which is relevant for the P versus NP problem question, is that they have polynomial time verification algorithms. We don't know whether they have polynomial time algorithms, but we know for sure that they have, each of them has a polynomial time verification algorithm. And what do we mean by a polynomial time verification algorithm? So we'll say that a decision problem has a polynomial time verification algorithm if whenever the answer for the given input is yes, so Hamiltonian cycle, yes, the graph has a Hamiltonian cycle, a Boolean formula, it is satisfiable. When the answer is yes, then there is a polynomial-sized proof of this fact. You can write out a proof that's quite short. Short is going to be polynomial in the size of the input that will establish that the answer is yes. And we have seen this for all of the 3 problems that we've looked at. Hamiltonian cycle, so if the graph did have a Hamiltonian cycle, what would the short proof be? It would be just show the cycle, as I did when I put those blue edges on top of the graph. You just have to, so once someone gives you such a cycle, you just have to verify first that it passes through every vertex of the graph. You can check that in linear time. And also that every edge that is shown in the cycle is in fact an edge in the graph, which again you can check in polynomial time. Okay? Similarly, traveling sales, TSP, the short proof is the Hamiltonian cycle, which has small cost. And again, that was something I showed you. We saw that example, and then we saw that I showed you that there was that cycle that had a cost less than the budget. And you could verify, once I gave you the cycle, you could verify that it was correct in fact, a linear amount of time. And similarly for SAT, the proof would be, if the formula is satisfiable, the proof will be the actual x equals 0, y equals 1, z equals 1, and you plug that in and verify in linear time that in fact that is satisfied. Okay? So all of the 3 problems we've seen so far, even though we don't know how to solve them in P, they do have polynomial time verification algorithms. And now that's all that we need to define NP. So NP stands for non-deterministic polynomial time, and NP is the class of languages that have polynomial time verification algorithms. So P was the class of languages that have polynomial time algorithms, methods that actually solve the problem. NP is the class of languages that have polynomial-sized proofs for, first of all, it's decision problems. The answer is yes or no. So it has polynomial-sized proof if the answer is yes. Okay. And so that is the P versus NP question. So is P equal to NP basically asks, is it the case that if a problem has a polynomial-sized proof for yes, a decision problem has polynomial-sized proofs for yes instances, it follows that the decision problem actually has a polynomial time algorithm. Yes or no? And we'd like to resolve it. We would love for it to be yes, because it will help us to solve a lot of problems. But quite apart from that, we'd like to know which way it goes. And notice, by the way, that every language in P is automatically in NP. Because if you have just run the algorithm on the input, and the answer comes out yes, just the execution of the algorithm on the input is of polynomial size, and that is the proof that the answer is yes. So P is automatically contained in NP. The question is the containment proper, or are they just equal? Okay, so that's basically the P versus NP question. But there is some there's some important additional structure that comes to this problem through the notion of NP completeness. So what is NP completeness? So this first part in here is the definition of NP completeness. So a language is NP complete. First of all, it has to be in NP. So it has to have this polynomial-sized proof for yes inputs. But additionally, it has to have this very strong property in here, which is that for every other language, L prime in NP, you can transform, given any input to L prime, you can just transform that input to an input for L and solve the problem using L. So, and we denote, so every language L prime in NP can be transformed to L in polynomial time, and we denote it by this symbol here, L prime polynomially reduces to L. And let me give an example, because in some cases this is quite easy to see. And let's consider, I want to show you that Hamiltonian cycle polynomially reduces to traveling salesman, TSP. HC polynomially reduces to TSP. So here's an arbitrary input to HC. And what I need to do in order to transform HC to TSP is to convert this input into an input for TSP such that the yes or no answer for TSP will give me the yes or no answer for this problem. And since those two problems are fairly similar, it's not too difficult to see how to do this. For instance, I can do this by just giving a cost of 1 for every edge. And then the budget I will give is the number of vertices in the graph. In this case, it's 5. Okay? So if this graph has a Hamiltonian cycle, with these costs, it will have a traveling salesman solution with cost equal to 5, in fact. And so the answer will be yes. And of course, if the graph does not have a Hamiltonian cycle, you're definitely not going to have a solution to TSP either. So this is a simple example of transforming one problem to another. And clearly, this was a polynomial time transformation. For any given input in polynomial time, I transformed it into an input for traveling salesman. However, of course, the definition for NP completeness doesn't just say transform one problem to another. It says every language in NP should be transformed to this given language L in polynomial time. Only then is the language NP complete. So you may wonder, is it at all possible that a language can be NP complete? And that's the celebrated Cook's theorem from 1971. And he showed that SAT is NP complete. SAT is the satisfiability problem that we looked at. Given a Boolean expression, is there an assignment of zeros and ones to the variables that causes the formula expression to evaluate to 1? And Steve Cook, he's a professor at Toronto and a very distinguished computer scientist. And he's the winner of the Turing Award, which is like the Nobel Prize for computer science. So, and certainly Cook's theorem is where the P versus NP question was formulated, because he showed that SAT is NP complete, and he asked the question, can it be solvable in polynomial time, in which case, all of NP would equal P. So that is where the P versus NP question was formulated. And independently, the same question was formulated by Levin in the Soviet Union, who showed a different problem to be NP complete, a certain tiling problem to be NP complete. So this problem actually arose independently in 2 places. And it's not difficult to see the following fact, which is what makes NP completeness so important. P equals NP if and only if an NP complete language is in P. Now, and the reason for this is because of the second property in here. If an NP complete language is in P, then you can solve any other language in NP in polynomial time by just transforming it to the NP complete language, and then using the algorithm for the polynomial time algorithm for the NP complete language to solve that other problem in polynomial time. Okay, so if an NP complete language is in P, then P equals NP. On the other hand, if an NP complete language is not in P, clearly P is not equal to NP because you found a language that's in NP that's not in P. And so as a result of this, this shows that in order to resolve the P equals NP question, you don't have to find a polynomial time algorithm for each individual problem in NP. Instead, you can just concentrate on the NP-complete language, and if you can find a polynomial time algorithm for, say, SAT, then you've basically shown that P is equal to NP, or conversely, if you show that it cannot be solved in polynomial time, of course, always you show P is not equal to NP. Now, a year later in 72, Richard Karp came up with a very influential paper in which he showed 21 problems to be NP-complete, which are indicated. This is taken directly from his paper, and he's shown these problems in the form of a tree. And here is Richard Karp. He's another very distinguished computer scientist and winner of the Turing Award. And what this tree indicates is basically, if you have a line going downwards from one language, one decision problem to another, it means that this problem has been transformed in polynomial time to this problem. And if this problem is already in NP, and all of these problems are in NP, such a transformation automatically establishes that this other problem is NP-complete, and that's simply because of the transitivity of these transformations. So already we've shown, Cook has shown that satisfiability is NP-complete, which means every problem in NP can be transformed in polynomial time to satisfiability. Now, if I show that just this one single problem, satisfiability can be transformed in polynomial time to 0, 1 integer programming, then through transitivity, I've also shown that every problem in NP can be transformed in polynomial time to 0, 1 integer programming. So this becomes NP-complete. And you can do this any finite number of times. So this tree can become larger and larger as long as each of these individual lines represents a polynomial time transformation. The NP problem at the other side of it becomes an NP-complete problem. So he showed these 21 problems to be NP-complete, and these problems basically represent most of the problems that people were wrestling with in the 60s and early 70s. When people were trying to get fast algorithms, they were not getting it, and they were just unable to figure out why that was the case. And he basically took all of those important problems, and these problems arise in industry. They arise, for instance, in VLSI design, in manufacturing. You need to optimize something, and there's an associated NP problem with it. And there's this whole bunch, and with this one very influential paper, he pointed out the enormous importance of the P versus NP problem, and the question really took off from that point on, because basically he showed that most of the problems that people were actually struggling with are in fact in this notorious class, that's NP-complete problems. Okay, so there are many very big, and you can see that our Hamiltonian cycle problem is also in there. So he showed that that problem is NP-complete. And of course, we have already seen that now. I just showed you that Hamiltonian cycle can be polynomially transformed to TSP. So again, by the transitivity, that means TSP is also NP-complete. So all the three problems that we've looked at that are in fact NP-complete problems. So if any one of those problems, or in fact any one of these 21 problems, if you come up with a polynomial time algorithm for it, you've shown that P is equal to NP. Okay? And interestingly, in his paper, Karp also mentioned 3 problems that people were struggling with that he couldn't show to be NP-complete. It requires ingenuity. By the way, it's easy to draw a graph, draw a picture like this. And in fact, the transformation from Hamiltonian cycle to TSP was quite simple, and I showed it to you. But some of these transformations are quite tricky and requires quite a bit of thought. Okay, so he, in his 72 paper, Karp expressed an inability to show the NP-completeness of these 3 problems. These were problems for which people had not come up with polynomial time algorithms, and still he couldn't come up with the reduction or the transformation that would show them to be NP-complete. And interestingly, the first 2 problems, we still don't know. We don't know of polynomial time algorithms for them, neither do we know, neither has anyone shown them to be NP-complete. And if I have time, I'll talk a little more about them later in my talk. Linear inequalities is just the decision version of the famous linear programming problem. And this is a problem that has the simplex algorithm was around at that time, but that was worst case exponential. And this is one problem which 7 years later in 1979, was shown to be actually in P. And that was through the ellipsoid algorithm of Kachin. So, so when you see a result like this, you may go back to thinking that maybe the reason why we haven't found polynomial time algorithms for these other problems is that we've just not thought enough about it, or deeply enough about it, or with enough brilliance about it. Because this was a problem that people tried very hard to find polynomial time algorithm, and it resisted that for quite a while until it was finally shown in 79 to be in P. But these two are still open. Yeah, okay. So I don't think I'm going to define it. Okay. So that was the P versus NP question. And I want to talk about various aspects of this problem. Oh, but first let me talk about the fact. So I mentioned that CARP came up with 21 NP-complete problems, and that showed that this concept was not just about Boolean satisfiability, but there were a lot of commonly occurring problems that are NP-complete. And a few years later, there's this very nice book, and if you're interested in knowing more about this topic, I think this book is still very relevant, even though it was written more than 20 years ago. A book on NP-completeness, Computers and Intractability by Gary and Johnson. And that book has a very valuable appendix. And already in 79, there were over 300 NP-complete problems. And these are not artificial problems. These are very natural problems arising from applications or arising from very basic principles. And a rough estimate is that currently there are tens of thousands of known natural NP-complete problems occurring from different domains. They're just cropping up all over the place. And huge collection of them, all just hoping to be resolved and hoping to get efficient algorithms, but no one has succeeded so far. Okay. Now, NP-completeness has been talked about quite a bit, in the popular media, and there's a common misconception about NP-completeness that I'd like to clear up here. For instance, here's a quote from a 1979 article in the New York Times. And this was actually an article, in fact, about linear programming. It came out soon after Kachin came up with this polynomial time algorithm, so it was talking about linear programming, but incidentally, it was talking about NP-completeness, and of course, as usual, it was equating NP-completeness with solving the traveling salesman problem, which is fine, because that's one of the NP-complete problems. But then it goes on to say, such problems are among the most intractable in mathematics. And of course, we did say that a problem is intractable if it doesn't have a polynomial time algorithm, but this is not saying that. It's saying among the most intractable in mathematics. So let's examine that statement. So are NP-complete problems the hardest problems to solve? And answer is an emphatic not at all. And because, first of all, we noticed for the three NP-complete problems we looked at, that is Hamiltonian cycle, TSP, and Boolean satisfiability, each of them can be solved in exponential time. If the size of the input was n, we could solve them in 2 to the power of polynomial in n. It is, in fact, close to 2 to the n multiplied by some small polynomial factor, certainly 2 to the power of polynomial in n. And in fact, the P versus NP question is still open, so it's quite possible that, in fact, all of them have feasible algorithms. So they could all, in fact, have polynomial time algorithms. And on the other hand, we know of more difficult problems. There are provably exponential time algorithms, provably exponential time problems. For instance, deciding the theory of Pressburger arithmetic, which is just the theory of the natural numbers with addition. That you can provably show that it takes at least doubly exponential time, not merely exponential time, 2 to the c of n, okay, which is a lot more than any NP-complete problem. We can solve all NP-complete problems much faster than this with an explicit algorithm. And even further, there are in fact problems that are undecidable. That is, you cannot design any algorithm to solve such problems. For instance, the halting problem for Turing machines. And let me just talk briefly about Turing machines, because the original P versus NP question was formulated in terms of Turing machines. Turing machines are named after Alan Turing. And again, a very distinguished mathematician, logician, and also computer scientist. In fact, the Turing Award is named after Alan Turing, because he formulated the Turing machine and the halting problem. And okay, so Turing machine is really a very primitive computing device, extremely primitive. It was proposed in 1936, before there were actual computers around. And Alan Turing proposed this machine as a device that can compute, that can serve as a computer. And it just consists of a tape and a simple controller, a finite controller that just scans the tape cell at a time. And when it scans a tape cell, depending on the state that it is in, and it has a finite number of states, and depending on the symbol it's scanning, it takes its action, which would be that it may change the symbol here, it may move left, it may move right, and it may move into a new state. And it just keeps doing that. And so the way this transition is specified in this finite control determines the algorithm, the mechanism by which it's going to move along the tape. And a Turing machine would compute a problem by just having the input. If the input is of size n, the first n cell tapes will contain the input, and then you let the Turing machine get started, and it'll have the output in a desired position. Say, if it's just a yes/no question, it'll replace the first symbol with the correct answer, 0 or 1, when the computation is completed. And here is the famous Church-Turing thesis, and Church was Turing's supervisor at Princeton when he was a graduate student there. A decision problem is decidable. That is, it has an algorithm. So a decision problem is decidable if there is some algorithm for it. At this point, we don't care about the running time. Just some method that correctly answers yes or no on all inputs. And a decision problem is decidable if and only if there is a Turing machine that solves a problem, a primitive device like this that solves a problem. Of course, nowadays, we will not deal with Turing machines in practice because our computing devices are a lot more sophisticated. But it turns out that they are, in this sense, equivalent to a Turing machine. Whatever can be computed on a modern computer is the same as what can be computed on a Turing machine. It may take a bit longer on the Turing machine, but the class of decision problems that you can solve is the same. So this thesis has really stood the test of time. And so in the context of this thesis, which I don't remember exactly when, probably in the 30s too, that it came, P versus NP can be just viewed as, analogous to the Church-Turing thesis, but in relation to efficient computation. So rather than just can it be computed, you're asking can it be computed feasibly in polynomial time. And interestingly, what can be computed polynomially, in a suitable abstract model that describes present-day computers is the same as what can be computed in polynomial time on a Turing machine, even though this machine is so primitive. I mean, it is slower. It's only slower, say, by a quadratic factor or so. So if you keep it as polynomial time, it remains the same whether you use a Turing machine or a modern computer. Okay? So in this context, when I said that the halting problem for Turing machines is undecidable, in a more modern terminology, what is undecidable is the question of, given a computer program and an input to that program, will that computer program halt? That is an undecidable problem. You cannot design an algorithm that can take an arbitrary program and an input to the program and determine if the program will halt on that input. Okay? So you just cannot design any algorithm at all for it. So when we talk about P versus NP and NP-complete problems being intractable, we should put it in the proper context. Yes, it's intractable in the sense that at present we don't have practical algorithms for it, but by no means are they the hardest problems to solve. Okay. Let me talk a little bit about consequences. So, we have here we have an open question here, P versus NP, and it could get resolved either way, either P not equal to NP or P equal to NP. And most people think P is probably not equal to NP. So let me take that, because there are less dramatic consequences. P not equal to NP, basically life will go on as usual. There are a lot of these important problems that we would very much love to solve in polynomial time. We don't know how to do it. And sure enough, Well, it's been proved that you can't do it. So we have to live with what is already fact for us. But also there's this interesting consequence if P is not equal to NP. It will have to be the case that there has to be a large number of problems that are neither in P, they're in between P and NP complete. That is, they are in NP, but they're not NP complete and they're not in polynomial time. They're somewhere in between. Okay? So an infinite collection of different classes of problems will have to lie between problems in P and NP complete problems. So I've already told you, we've identified tens of thousands of natural problems that are NP complete. And there are, I would say, easily that many in P, because that's been quite an active area of research coming up with efficient algorithms for natural problems. So we have tens of thousands of problems in P, tens of thousands of NP-complete problems. So what are problems that lie in between here? If P is not equal to NP, there should be tons of problems between the two. Surprisingly, there are very few natural problems in that in-between class. And I've listed the three most well-known ones. The first two are really complements of each other. Given a positive integer, is it prime? The second is given a positive integer, is it composite? That is it not prime? That means, does it have two non-trivial factors that multiply to give the product? Now, at first sight, it may seem that prime is actually a polynomial time algorithm, right? I mean, so you're given a number n, try every number until square root of n, see whether any of them divides n. And if none of them divides n, it's prime, otherwise it's composite. Now that's definitely a correct algorithm. The one problem is that it's not a polynomial time algorithm. Because if you're given a number whose value is n, the size is the number of digits in the number. And that's just log to the base 10 of n. So it's only logarithmic in n. The size of the input is logarithmic in n. So if you have a square root of n time algorithm, that's not a polynomial time algorithm. Okay? So the naive algorithm is not polynomial time. There are other faster algorithms known, but none that run in polynomial time for primality or for compositeness. There are randomized polynomial time algorithms for both primality and compositeness. And now if you go to the actual question in the case of compositeness of factoring a number into its prime factors, that is considerably harder. It is, I mean, none of them are in polynomial time, but that problem seems to be the best algorithm for that problem takes considerably more time than just determining if a number is prime or composite. And in fact, it's hard on the average, even if you take a typical, if you say a problem is hard, it means that for each input size, there's at least one input for which it's hard, but there may be other inputs for which it might be easy. And in the case of factoring, it's in fact hard on the average. It appears to be hard on the average. At least all the algorithms that we've had resist factoring large numbers in most cases. I mean, they take a long time to factor most numbers. And the third problem in here, now one other point I want to say about these two problems is that we think that neither of them are NP complete. The reason is that they're complements of each other, and they are both in NP. By the way, these two problems were in Karp's 72 paper, but this wasn't. And the reason it wasn't, he had stated it as non-primes rather than primes. The reason is, at that time, it was not clear whether primes was in NP. How would you test if a number is prime? It's easy to test if a number is composite. The polynomial-sized proof would be to just give the factors, two factors, and then we know that multiplication is in polynomial time. Show that if you multiply them, you get back the original number. But how do you show that prime is in NP? You want a short proof. And that came a few years later. So that's one of the few examples where showing the problem to be in NP was not very easy. In most cases, it's very easy to show that a problem is in NP, but this required some little input from number theory. But it's not very difficult, but it's not very easy either. But in fact, both these problems are in NP. So you have two problems that are complements of each other that are both in NP, and that's not known for NP-complete problems. If you take any, like for instance, Hamiltonian cycle, that's an NP. But what about the complementary problem? Given an input graph, is it the case that it does not have a Hamiltonian cycle? And we don't know of any polynomial-sized proof to demonstrate that fact. The only way we know how to demonstrate that fact for an arbitrary input is to basically show that try all permutations And in every permutation, there's one edge missing. Hence, there's no Hamiltonian cycle. Okay, so there is this difference. For NP-complete problems, so far, we don't know of any complement of an NP-complete problem that's also in NP. While here you have complements that are both in NP, so we think that these are not NP-complete. And graph isomorphism is, I don't think I have the time to go into that. It's a very interesting problem, and it's, let me just flash this slide. So in this problem, you're just given two graphs, and you want to know, are they really the same graph? Can I just match the vertices in this first graph with the vertices in the second graph so that the edges fall into place? And in this case, in fact, the answer is yes. And if I do this matching, the edges will fall right on top of this. And so the graphs are isomorphic. And we don't know how to solve this problem in polynomial time. Neither do we know that it's NP-complete. And here, again, there are certain reasons to think that it's not NP-complete. But the amazing thing is there are very few problems, natural problems, lying between P and NP-complete. So what would be the consequences of P equals NP? If P equals NP, and as a result, we actually get a feasible algorithm for an NP-complete problem, then there would be a lot of celebration, because an enormous number of very important problems will suddenly become tractable. And you'll be having, I think, enormous consequences in different walks of life as a result of this. But one thing that will hurt is public key cryptography, because, for instance, some of you might be using PGP signatures or PGP encryption for your email, and that system depends on, most of these systems use, for instance, the product of two large primes. And the security of the system is dependent on the fact that we don't know how to factor the product of two large primes. And if P were shown to be equal to NP by a simple algorithm for SAT, say, then we can use that along with the reductions to come up with a feasible algorithm for factoring. And that would destroy the security of public key crypto systems. And also, potentially, all of the solutions to the millennium problems can be found. The reason being that, if these problems had short proofs, and presumably that's what we are looking for, short, elegant proofs, you can phrase that as an NP problem. And P equals NP, well, use the reduction to SAT, use the algorithm for SAT, and thereby churn out the proofs of all of these problems. So that would be a wonderful situation. And I should mention, I had initially had this slide on before I started my talk. And this way of looking at P versus NP was actually formulated by Kurt Gödel 15 years before Cook precisely formulated the P versus NP problem. And Gödel was an extremely famous logician who's most famous for his incompleteness result. And von Neumann was a very wide-based, I guess, mathematician who's worked on a lot of different areas: mathematical logic, quantum mechanics, game theory, logical design. And also for computer science, he is the person who formulated the stored program, the idea of using a stored program for computers. That is, and what that is just storing the program just like data inside your computer. Before that, people used to view the program as something separate. And he did this in the context of programming the first general purpose computer that was built. That was an ENIAC in the University of Pennsylvania in the 40s. And soon after that machine was built, it was given to the army. And von Neumann was one of the people who was helping to code it up to solve problems. And they were finding it very cumbersome to, each time you wanted to change the program, it was a huge effort because the program was separate from the data. And he suggested the stored program model, which is universally stored program approach, which has been universally used since then, and is an extremely important contribution to computer science. But this letter was written when von Neumann was really pretty much in his deathbed. And so you can see that he asks after his health, but pretty soon goes into something mathematical, which probably was much nicer for von Neumann than any letter that just talked about the health and weather. But here, what I've highlighted in blue, he's basically asking this question, which can be seen as a version of the P, something relating quite similar to P equals NP. So what he's saying is, and here, where he talks about a formula in the predicate calculus, we can think of it as just a mathematical conjecture. Okay. So it is evident that one can easily construct a Turing machine which, for each mathematical conjecture and for every natural number n, would allow one to deduce if f has a proof of length n. So what he's saying is you can use brute force. So if it has a proof of length n, try every possible proof of length n. So in time exponential in n, you can either say, yes, it has a proof of length n, or rule it out absolutely. Okay? But now he goes on. So let psi of fn be the number of steps that the machine requires for that. So this particular machine that solves that, and phi of n be the maximum of this psi over all mathematical conjecture. So the worst case time that it takes to determine if some conjecture has a proof of length n. The question is, how fast does this worst case time grow for an optimal machine? So one can show that it has to be at least linear. If actually there were a machine with it being linear, phi of n being k times n, or even quadratic, so he's already got the germ of a notion of polynomial time, this would have consequences of the greatest magnitude. So it's interesting to see that this question has been looked at even before it was actually gained prominence. So I think I just have a couple of minutes. So I'm going to very quickly talk about the approaches that have been used to solve P versus NP. Well, if you wanted to show P equals NP, you have tens of thousands of problems that you can work on. You can take any NP complete problem and try to come up with a polynomial time algorithm for it. And if you succeed, you've shown P equals NP. And many people have tried. And there have been many erroneous proofs of this, so-called proofs. And that's not surprising, because when you think of how similar the Hamiltonian cycle problem and the Euler-Tour problems are, it's not surprising that people may think that they've got a polynomial time algorithm, they make some slip up somewhere, and apparently with the Minesweepers problem, there's been a new surge of erroneous or surge of so-called proofs of P versus NP. I was talking to Steve Cook just last month, and he said that he's in correspondence with a couple of people who've told him that they've solved the Minesweepers problem in polynomial time, including one doctor who will not send him his proof for fear that he would steal it and take the $1 million. So we'll have to see. Now, since most people think that P is not equal to NP, how would we go about showing that? Now, that's quite a bit harder. And the normal method of showing that, especially in a case like this where P is a subset of NP, to show that NP is a larger class, is a certain method called diagonalization. But there is reason to believe that diagonalization will not work for this problem, and at least not in the way that it has been used in other contexts. So most of the work on P not equal to NP right now is concentrated on lower bounding the size of Boolean circuit families that you can represent any algorithm by a Boolean circuit family. And that makes it very combinatorial. And if you can now show that this circuit family has a super polynomial size for an NP-complete problem, you would have shown that P is not equal to NP. Sounds like a very interesting approach, but at this time we don't really have much results. We'll have to wait and see how this plays out. And I should also mention that the P versus NP problem is really, it's in here, but we have a whole lot of related questions, various resource-bounded classes of problems where log space is just a class of problems that you solve by just using a small amount of additional space, workspace, only logarithmic in the size of the input, while P space you use a polynomial amount of workspace. And it's not difficult to show by diagonalization that log space is a proper subset of P space. But in this entire chain in here, we don't know which of these inclusions is actually strict, and so this is a very intriguing question. And a related question is, as I pointed out, we don't know for NP-complete problems if their complement also lies in NP. So it's kind of a related question, is NP equal to co-NP? It would equal co-NP if P equals NP, because P is closed under complementation. But it could be the case that P not equal to NP, and yet it could be the case that NP equals co-NP. So there are lots of related questions. So I'd like to conclude now with some predictions from, so I asked Steve Cook, who proposed the P equals NP question, and Richard Karp, who made it, who brought it to prominence, what they thought, how this would play out. And Karp says that he conjectures that the P versus NP problem will be resolved one way or the other by a mathematician under 30 using an approach that nobody has thought of. So all you graduate students out there should get your paper and pencils handy. And Steve Cook says, I conjecture that someone will give a sound proof that P is not equal to NP sometime in the next 20 years. So it's very optimistic predictions, and we'll have to see how it plays out. Thank you.
Are there any questions?
I've read in the news about people who use flowing fluids or DNA, principles of quantum physics to solve NP problems in polynomial time. Is there truth?
Well, quantum, yeah, as far as quantum computing is concerned, there's a very celebrated result. I talked about factoring, which we don't know is in polynomial time. And in fact, it seems to be hard, even harder than compositeness, which is not known to be NP. So factoring is actually not a decision problem. It's, so the associated decision problem is compositeness, is a number composite. And that's not known to be in P. However, if you use quantum computers, you can solve it. So that's the result of Peter's show, that factoring is in quantum polynomial time. However, we don't know about any NP-complete problem that can be solved in polynomial time using quantum machines. Now, yes, there have been results about DNA computers and so on, but you can view them as massively parallel systems. And here we are dealing with a single processor, a sequential processor. And so it falls outside the framework of what we are talking about here. So,
yeah.
Actually, my question was very similar to his, but I want to ask sort of a follow-up. Is that if you find a quantum computer program that solves an NP-complete problem in polynomial time, do you get $1 million?
well, that's not a question for me to answer.
When you build the quantum computer, maybe.
I should mention that there is some, there have been some results that show that, that many of the natural methods in which quantum computing algorithms have been developed will not give a polynomial time algorithm for an NP-complete problem. So, for instance, the type of techniques that put factoring in polynomial time are not going to show an NP-complete problem to be in quantum polynomial time. But of course, we don't know. There may be other new methods not yet known. We don't know.
And the answer to my question is?
It's not up to me to answer. I don't, yeah.
Is it true that you only use this with, as you said, decision problems?
Oh,
I thought
yeah.
in Karp's slide you should things like sequencing.
No, he formulated everything as decision problems. And the main reason we do it as decision problems is to get yes, no. So that the inputs for which the answer is yes is just a subset of all the inputs. And that's why you can talk about languages. However, as far as the P versus NP question is concerned, it turns out that that's not a big distinction. Because if you had, for instance, an actual search problem, you can formulate an associated NP problem that's a decision problem in such a way that you just have to make a polynomial number of calls to that decision problem in order to solve the search problem. For instance, I don't know, suppose, for instance, the traveling salesman problem. So typically what you want is a tour of minimum cost. You may have a budget, but you don't want to spend more than necessary. So what you're really interested in is an optimization problem, which is find a Hamiltonian cycle of minimum cost. Well, you can use the decision version that I've formulated. Is there a tour of cost less than B? And do a binary search. Okay? And you have some simple upper bound on a cost of a tour, which would be, say, n times the maximum edge weight. And then you start with that cost, and then try half, and keep searching that way. So a polynomial number of calls to an decision problem will solve the original problem, and that would still be a polynomial time algorithm. So in terms of actually getting polynomial time algorithms for actual problems that are not decision problems, it's really an equivalent question. And we use decision problems mainly because then we can talk about subsets of all the inputs for which the answer is yes. Yeah.
Is it possible that the P versus NP problem is undecidable itself?
Possible? I mean,
And if it's so, we still get to really know it.
That's true for all of these problems. And in fact, Hilbert's 10th problem was shown to be undecidable. But most problems tend to have a yes or no answer. So we have to assume, unless someone proves that it's undecidable, we'll just have to think it can be resolved.
What do you think?
Well, I defer to the experts. I'm impressed that both Cook and Karp think that it's going to be solved soon, and so I'm just waiting for it to happen.
Well, maybe if there are any newcomers to the series tonight, let me remind you there are refreshments down in the eating area that way and downstairs. And the next talk, the fourth one, is in 2 weeks from tonight. And I hope we see you all here then.